Hello, my name is TTJ Kepsi Richie. Welcome to my online class. Today, we'll be discussing ordinary differential equations. And before the video ends, we will learn how to find the WRONSKIAN of two functions as well as three functions. Then with our idea in finding the WRONSKIAN of a function, we'll learn how to describe the nature of solution to first order ordinary differential equations. This will be a very interesting engagement, I promise you. So please take a seat. So if we have two functions, say f of x and g of x, and we are asked to find the WRONSKIAN of this function. The WRONSKIAN of the function, we write it as w f comma g. So if you see this, it means the WRONSKIAN of the two functions. It will just be equal to the determinant of the two functions, f of x, g of x, and their derivative. That's f prime of x and g prime of x. So this is how we find the WRONSKIAN of two functions. So when they give you the function, the differential of the function under it, another one, the other function, the differential of that under it, then you find the determinant. That becomes the WRONSKIAN of the function. So let's look at an example. They say find the WRONSKIAN of the function f of x equal to cos x and g of x is equal to sin x. So how do we do that? The WRONSKIAN of f comma x will be equal to the determinant of cos x sin x. Then we differentiate cos x. When we differentiate cos x, we get negative sin x. And when we differentiate sin x, we get cos x. Now we find the determinant. So this will be cos x times cos x will be cos square x. Then minus negative sin x times sin x will be minus sin square x. So what are we having? We have cos square x plus sin square x. And cos square x plus sin square x is nothing but 1. So we can say the WRONSKIAN of the two functions f and g is equal to 1. I hope you get that. Now what of if it is three functions? How do we find the WRONSKIAN of that three functions? What if you have three functions? Let's say f of x, g of x, and h of x. How do we find the WRONSKIAN? The WRONSKIAN of the three functions f, g, and h will just be equal to the determinant of first column. You write a function f of x, g of x, and h of x. Then the second column will be the differential of each of the functions. The first differential of the function. So f prime of x, g prime of x, then h prime of x. Then the third column will be the second differential of the function. So f prime prime of x, g prime prime of x, then h prime prime of x. And remember, when we find the determinant, we know how to solve this. So the determinant will just be f of x, the determinant of what is not under the f of x. So that will be g prime of x, g prime prime of x, then h prime of x, h prime prime of x, then minus g of x, the determinant of what is not under the g. So we have f prime of x, f prime prime of x, h of x, then h prime prime of x. Then plus h of x, the determinant of what is not under the h. And what is that? F prime of x, f prime prime of x, g prime of x, and g prime prime of x. So after we do this, we just find the determinant. And that becomes the WRONSKIAN of the three functions. We take some sample question on this and see how we deal with it. So we'll look at how to find the WRONSKIAN of three functions. So now, let's say find the WRONSKIAN of the function f of x equal to e exponent x, g of x equal to e exponent 2x, and h of x equal to e exponent 3x. How do we find the WRONSKIAN? So the WRONSKIAN of f, g, and h will be equal to the matrix, the determinant of the matrix. First column will be the functions, that's e exponent x, e exponent 2x, and e exponent 3x. Then the second column will be the differential of each of the functions. When we differentiate this, it will be e exponent x. We differentiate this, we get 2 e exponent 2x. Remember, we just differentiate the exponent and use it to multiply the function. This will be 3 e exponent 3x. Then we find the second derivative. When we differentiate that again, we get e exponent x. We differentiate this, we get 4 e exponent 2x. Then we differentiate it, we get 9 e exponent 3x. Now what will be the determinant? The determinant will be e exponent x, the determinant of what is not under the e exponent x. And that's 2 e exponent 2x, 4 e exponent 2x, 3 e exponent 3x, then 9 e exponent 3x, minus e exponent 2x, the determinant of what is not under this e exponent 2x. That's e exponent x, then 3 e exponent 3x, then 9 e exponent 3x. Then plus e exponent 3x, the determinant of what is not under the e exponent 3x. That's e exponent x, 2 e exponent 2x, then 4 e exponent 2x. So we get e exponent x bracket, this times this, 2 e exponent x times 9 e exponent 3x, 2 times 9 is 18, so we have 18 e exponent 5x. Then this times this will be 12, so minus 12 e exponent 5x. Minus e exponent 2x bracket. This time this will give us 9 e exponent 4x minus 3 e exponent 4x. So remember, these are indices. When they are multiplying with the same base, you just add the exponent. Then plus e exponent 3x bracket. This time this will be 4 e exponent 3x minus 2 e exponent 3x. So we'll simplify that further. We'll get e exponent x bracket 18 e exponent 5x minus 12 e exponent 5x will be 6 e exponent 5x. Then minus this one to e exponent 2x. 9 e exponent 4x minus 3 e exponent 4x will be 6 e exponent 4x. Then plus e exponent 3x. 4 e exponent 3x minus 2 e exponent 3x will be 2 e exponent 3x. So what do we do? This multiply again. Remember, the bases are the same. We can just add the exponents. So we'll get 6 e exponent 6x minus 6 e exponent 6x, then plus 2 e exponent 6x. So this minus this is 0. The final answer will be 2 e exponent 6x. So we can say the WRONSKIAN of f, g, and h is equal to 2 e exponent 6x. So having known how to find the WRONSKIAN, we are going to describe the nature of solution to ordinary differential equations, first order for that matter, using the WRONSKIAN. So having known how to find the WRONSKIAN of 2 functions and 3 functions, we are going to use that idea to describe the nature of solution to higher order ordinary differential equations. So how do we do that? If you find the WRONSKIAN of a particular a solution to a differential equation, let's say f and g, and it is equal to, you find two situations, when it is equal to 0 and when the WRONSKIAN is not equal to 0. When the WRONSKIAN is equal to 0, that means the solution is linearly dependent. And when it is not equal to 0, that means it is linearly independent. So when we find the WRONSKIAN and it is equal to 0, that means it's linearly dependent. And when it is not equal to 0, it's linearly dependent. So let's see a example here. They say the general solution to a particular differential equation is given as y equal to a e exponent 2t plus b e exponent 4t. Describe the nature of solution. So this one, the solution is given. There are some situations where you have to solve it yourself and describe. Please check out my videos on how to find solution to homogeneous higher order ordinary differential equations on YouTube. So, how do we describe the nature of this solution? We let f of t to be equal to e exponent 2t, just the function. We forget a constant. Then g of t to be equal to e exponent 4t. What do? We find the WRONSKIAN of f and g. Remember, it to be equal to e exponent 2t, e exponent 4t. Then when we differentiate this, we get 2 e exponent 2t. And this will be 4 e exponent 4t. So we find a determinant. This times this will be 4 e exponent 6t minus this times this, so minus 2 e exponent 6t. This minus this will give us 2 e exponent 6t. And this is not equal to 0. Then we say that the nature of solution to the equation is linearly independent. Since it is not equal to 0. I hope you get that. We saw one more example on this so that you'll be abreast with the concept. So we saw our second example on this. Please remember to subscribe to my YouTube channel to make it grow. This will make YouTube suggest my channel to other users and to make my channel grow, and I can record more mathematical content for you. So you can pause the video and try solving the question on the board. They describe the nature of solution to the differential equation given as y equal to, that's the complementary solution, is equal to 4 e exponent negative 2t plus 6 e exponent negative 2t plus 1. So how do we do this? So remember, we let our f of t to be equal to the function. Ignore the constant. E exponent negative 2t. Then g of t equal to e exponent negative 2t plus 1. What do we do? We find the WRONSKIAN of f and g. The WRONSKIAN will be the determinant. We have e exponent negative 2t, e exponent negative 2t plus 1. When we differentiate this, we get negative 2 e exponent negative 2t. And when we differentiate this, we get negative 2. So negative 2 e exponent negative 2t plus 1. We find the determinant of that. So this will be equal to this, multiply this, we get negative 2 e exponent negative 4t plus 1. So then minus negative 2 e exponent negative 2t times e exponent negative 2t plus 1 will be negative 2 e exponent negative 4t plus 1. What do? We get negative 2 e exponent negative 4t plus 1, then plus 2 e exponent negative 4t plus 1. And this is equal to 0. So negative 2 plus 2 is 0. Then we can say the WRONSKIAN, since the WRONSKIAN of f of is equal to 0, the solutions are linearly dependent. I hope you get that. So we'll end it here today. Please remember to subscribe to my YouTube channel before you sign up. Until we meet again, my name is TTJ Kepsi Richard.